Hey there, my propositional people. In the next 5 videos, I'm going to be talking about a couple different inductive propositions. Um, so, a bit of terminology that we're going to come back to later in the course is relation. So, what we've said is like any function into prop, like nat arrow prop or whatever, like EV is a nat arrow prop, we say is a property as opposed to a predicate, right? Like nat arrow bool is a predicate. These are arbitrary terms. It's just what we're using in the course. A two or higher argument proposition defines a relation, right? In fact, a property, as we've seen it so far, is what we would call a unary relation. And then other relations are, say, binary or even ternary / trinary relations, catenary relations, and so on. So you've already seen binary relations. One binary relation is equal, right? Things that are like equality is a binary relation. I can show you the type real quick. Let's do this. Right? Eq, this is the same thing as, equals, is A arrow prop for any type A. Okay, so another binary relation that you've probably heard of is less than or equal to. So we've already defined LEB as a predicate. Give me two natural numbers and I'll compute a Boolean that says yay or nay is one greater than the other. But we can also define an inductive proposition. Using the inductive proposition will come with the usual benefits of an inductive proposition. We'll get to reason only about the cases we care about, and we don't have to worry about some computation order. We simply define the notions of evidence we have, and then things exist. Now, okay, it's not computable, it's not a thing you get to program with, but we'll get to eventually, as you see, prove some if and only if relationship between our definition of less than or equal to and the LEB predicate. Let's get started. Let's look at the inductive proposition. Okay, how does it work? LE less than or equal to, that's what we're going to call it, is a binary relation. You give me a nat, and I'll give you back a proposition. And it says, okay, well, my first rule is this axiom, LEN, which says that for any natural number, n is less than or equal to n. So we're going to read this left to right. N is less than or equal to n. LES says, well, for any pair of natural numbers n and m, if I know that n is less than or equal to m, then n is certainly less than or equal to the successor of m. That is to say, you can always sort of add one to the greater thing, and the inequality still holds. And then next up, we'll say n less than or equal to n. Let's use that notation. Let's use the conventional math notation for this. Okay, so let's play around with it. Let's see what we can do. A great exercise, if you like, before we even start doing any of these proofs is convert this to inference rules. Right? In my mind, that's what I do. Whenever I see an inductive definition like this, I convert it to inference rules. Another great thing to convert it to would be implications, right? What's the implication here? Like, what's the theorem LEN? What's the theorem LES? Right? Both these are great to do. They're going to really help you do your work. Okay, let's do some test proofs. So, for example, 3 should be less than or equal to 3. Everybody agree? Seem reasonable? People feel good about that? Okay, cool. So how might we prove this? Well, we have LEN or LES. LEN says every number is less than or equal to itself, and here we have the same numbers, so great. LEN. Looks good. Okay, great. That seems like a true fact, as the kids say, and it seems to work for me. Okay, here, what can we do? LEN doesn't yet apply, right? LEN is in a certain sense our base case, right? For just the one thing. So LES says well, to show that n is less than or equal to m, it suffices to show that n is less than or equal to 1 less than it. So, for example, to show 3 is less than or equal to 6, it suffices to show that 3 is less than or equal to 5. To show that 3 is less than or equal to 5, it suffices to show that 3 is less than or equal to 4. To show that 3 is less than or equal to 4, it suffices to show that 3 is less than or equal to 3. And now I could say LEN and finish my proof. Or I could say test LE1 and finish my proof. Either way. At this point, you may notice there's a bit of a pattern here, right? To prove that a number is less than or equal to another, there's going to be some number of LESs to kind of like bring the greater one down to the level of the other, and then you say LEN. Right? So it has this sort of like chain-like or linear structure, like it's a tower, like many other derivations we've seen. So, great. Okay, let's go the other way. What if we assume something false with LEN, right? If 2 is less than or equal to 1, bear with me, then 2 plus 2 equals 5. Granted, If you assume something wrong, right, because 2 should not be less than or equal to 1, then you can conclude something wrong. I'm fine with that. If you're willing to admit bad assumptions, then I'm fine with you getting bad conclusions. Garbage in, garbage out. Okay, so what do? Well, we could ask, hey, I don't believe 2 less than or equal to 1. Can you tell me how that came to be? Okay. Oh, inversion. Oh, so much stuff. Well, let's look though. So one thing we could do, maybe you're just on team subst. Okay, that's actually not so bad. Right? Bunch of crap. N and M vanished. Right? They're gone. It's like fair enough. The N and M don't actually get mentioned anywhere. These are like artifacts of how inversion is working. So we subst away, and now we just say, okay, H1, 2 less than or equal to 0. All right. Not bad. All right, let's keep going. Huh. Why is that? Why did that work? Well, 2 less than or equal to 0, which constructor could have applied? It couldn't be LEN because they're not the same number. Could it be LES? Well, no, because you would need to have a successor here to be able to have a derivation about something smaller, but there's no way that could have worked either. So again, inversion does its job beautifully, saying like, look, neither of the rules could have applied here. This is false. You're done. You love to see it. Okay. Returning to the topic of encodings, I just want to conclude by saying, okay, we can define less than as a relation in terms of LE. Right? We saw this when we did it for AX, but we've done it since then for things like LTB and GTB and so on. This is a nice way to do things. You might be surprised because we could define our own inductive that did something else, right? That's a good exercise, great practice. Can you adapt this inductive definition so that it defines LT rather than LE? And you can. But it turns out it's much more convenient to have one mathematical notion and then encode related ones in terms of it than it is to have 2 separate ones and then have to prove a bunch of theorems saying like, okay, look, they're almost exactly the same. You have LT, if and only, you have LE, if and only if LT or equal, right, and do all that. But here, it actually ends up just being simpler to say, look, less than is just a macro. We turn all of our less thans into less than or equals to's. And you can kind of check this logic on your own to see whether or not that makes sense to you. Okay. That's it for less than or equal to. We're going to spend a lot of time talking about less than or equal to. It's actually it's really important for the case studies we're going to do. And I think it's also just a really nice example to think of. But I've got a couple videos coming up where we're going to look at a couple other inductive relations. You can actually see one peeking through on the bottom there, though. Okay, talk to you soon.